Welcome back to our online lecture course on statistical mechanics, chemistry, and material science. Today, we shall start a new topic, a very important topic, which is the computer simulation methods in statistical mechanics. As we have seen, we have gone through many aspects of statistical mechanics from the beginning of the postulates and then on to different ensembles and applications. And one thing that you must have realized also, that it's a lot of analytical work, a lot of very difficult mathematical methods that are being implemented. And these mathematical methods and the requirement of mathematics becomes more and more demanding as you go to real systems. Actually, at one point, it becomes quite difficult. And so one then starts wondering that can one really push this ambitious project of statistical mechanics of explaining the observed variables of liquids and crystals, phase transitions, biological systems from first principles. From first principles, we mean that from an intermolecular potential, particularly when the intermolecular potential are complicated. So this was the condition state of the art in 1960s and 70s when people are still pursuing analytical work. By end of 1970s, it became quite clear that it might not be feasible to solve these analytical theories. For example, Farkas-Yavic equation or the partition functions to get the required observed properties. That was very that was beginning to dawn on people. Fortunately, at the very time, the computers were developed to a great extent, and some very smart people realized that computer simulation can come to rescue in a big way. And that was developed by very some artful techniques. And now computer simulation essentially the 90% of the applications of statistical mechanics that we do through computer simulation. However, the methods of computer simulations are firmly based on the developments of or advances of statistical mechanics even now. So this kind of handover basic, it seems like that statistical mechanics developed all the principles, the methods, and it was kind of handed over to applied to real systems, because in the analytical methods, solving of integral equation theories, or as you see in case of Maillard cluster expansion, we could get the phase transition, we could get some about the cluster size distribution, but even then the calculation of virial coefficients is extremely difficult for any kind of realistic potential. So in this slide we are going to kind of just state what I've been saying, that simple model based calculations can be done, and then certain simple theories like cell theories, lattice models like Ising models, Landau theory, mean field theory, they are wonderful theories. They have done a wonderful job in explaining and providing us insight of what is going on. However, they cannot be successfully applied to a quantitative prediction for the real systems, like water, liquid water, ethanol, proteins, and then DNA. So this kind of what we want to understand, the lipid bilayer. So all these systems, let us stick to basically with water, which is H2O, very simple thing. So even in water, analytical theories did not quite succeed, despite tremendous effort by very smart people. Well, we can do some amount of analytical thing to try to understand the liquid to steam transition, but even when it comes to freezing, it is still a very it has not been successful. So we faced with these things. As I told you, in 70s it was a bit realized, then people realized that, however, this bottleneck, the big wall presented by the analytical theories, which cannot deal complex intermolecular potential. What are intermolecular potential is complex in the sense is more than Lennard-Jones. It has oxygen atom through hydrogen, and they have charges, dipole moment. But then at that time, computer simulation came to big risk. And so these intermolecular potentials, which are discussed, like Lennard-Jones discussed a big way. And this is just radial potential between two atoms. And water is a far cry from these things. So real molecule quite far. So intermolecular potential for real molecular liquids like water, ethanol, dimethyl sulfoxide, many other things are far more complex. So analytical theories didn't work, and that is why computer simulation came to rescue. And as I said, 90% of the StatMech based work now done with using computer simulations. So in fact, it required no less ingenuity and no less creativity to develop the computer simulation techniques. Yes, basic principles and basic methodologies and the things that we need to calculate, like radial distribution function, specific heat from energy fluctuations, and many other quantities were indeed was the formalism and the way to think and go about, and the equations were given by statistical mechanics, but they are implemented now through computer simulation. So that's what I said, as if the methods of statistical mechanics was developed and handed over to the next generation to take it ahead by using computer simulations. So computer simulation, as I am saying, is needed very smart work, and it started essentially with a very famous paper. I'll cite the paper in the next slide by Metropolis, Rosenbluth, Taylor and Taylor, and they did what is called Monte Carlo simulation. That's an equilibrium static simulation, and a few years later in 1950s, both in 50s, Alder and Wainwright did this simulation in a time plane by molecular dynamics simulation, and both treated these hard sphere kind of interactions, which was simple to do, and got results which then was tested against the theoretical results, which fortunately were known quite a bit from analytical theories, because hard sphere is something analytical theories made some advances. So we then did computer simulations and then tested the computer simulation against the analytical theories. It served both the purpose. We could test the analytical theories, which, as I said, cannot be done exactly, but fairly accurately for hard spheres, and we can check computer simulations and played an extremely important role. That means this verifying computer simulation by statistical mechanics and verifying statistical mechanics by computer simulation, where you start from first principles. I give you intermolecular potentials, and you do computer simulation like molecular dynamic simulations, and you give me a bunch of numbers which now can be tested with theory that flows directly from statistical mechanics without going through the computer simulation. So they replayed this is something which is not sufficiently emphasized, that these two things are extremely important and extremely useful in both the ways. And while Alder and Rosenbluth did hard spheres, the fast continuous potential, and that was the birth of, one can say, realistic simulation of real systems, was done by an Indian, Anisur Rahman, who studied in Hyderabad and then he went to United States and made enormous contribution. Later teamed up with Stillinger, did a calculations of water. That those work went on a whole of 1970s. I think they have 8 or 10 papers, very nice papers, which is done through these computer simulations of then that became available in 1970s in increasing capacity. I should also mention the work by Karplas, Warshall and Levitt, who had given Nobel Prize in 2014 for their applications of these computer simulation techniques or computer methods to study of biology, and that was the is a celebration of the reach of computer simulation before that, no Nobel Prize on computer simulation was given. There were a lot of Nobel Prizes and recognition are given to analytical theories developed by statistical mechanics. So these are the papers I told in the slide that you need to look into. The slides are, the first paper should be the Metropolis Rosenwood, Taylor and Taylor, the equation of state calculation of fast computing machines, 1953. Then I stopped and they did hard sphere system. Then Barney, Alder and Wainwright, they did hard sphere and later hard disk. And first paper of Metropolis Rosenwood was done by Monte Carlo simulations, while Alder and Wainwright implemented and is the molecular dynamics simulation. So they are two different techniques, but the results agreed well with each other and with the theories as I have been telling. Then the real fast continuous potential was done by Anish Rahman, is a seminal paper and very famous paper in 1964, which is highly cited and highly respected. And then Rahman teamed up with Stillinger and did a series of work on water, and that at that time was increase the reach of computer simulation to a significant degree. And this is history. Now let us start on the main work, which is the classification of simulation and molecular dynamics simulation, computer simulation rather, divided into two things. One is molecular dynamics, which is propagated in time domain, and this Monte Carlo. So remember, when you are doing statistical mechanics, in the beginning, the postulates, we are telling there are two postulates of statistical mechanics. One is that equilibrium probability, another is the ensemble time average equal to ensemble average. Now, so the basic idea of statistical mechanics is that you have the phase space in particles, the 6 n-dimensional space called capital gamma space, and the system is executing a walk in this trajectory in this multidimensional phase space. And the properties that you observe as a result of this trajectory, as the motion of the system on this phase space. So if you want to do dynamics, that how the time they are correlated in time and also structure, then we have to really let the system propagate on the 6-dimensional space by moving each atom and molecule, because the movement in phase space is essentially due to the movement of each atoms and molecules, individual atoms and molecules moving, rotating, and that is so one point in phase space to another point in phase space means change of configuration. All this my in particle system, in molecule system, or in atom system. Monte Carlo, on the other hand, is dips on the ensemble. So molecular dynamics is time average. Monte Carlo is in the ensemble average. In Monte Carlo, there is no time. In Monte Carlo simulation, what we start with initial configuration, then we follow certain rules to generate new configurations. New configurations which are allowed according to Boltzmann distribution and some technique like that. But there is a lot of creativity in creating this Monte Carlo. As name Monte Carlo, which is a huge gambling town with lots of casinos in France, and this Monte Carlo is a method which is it depends on random number, repeated use of random number, and which allows us to push the system in the configuration space from one point in the configuration space to another configuration space, and there are rules so that the systems that we generate follow the basic principles of statistical mechanics. So the sampling is very important in Monte Carlo. So to summarize again, molecular dynamics is a time averaging, while Monte Carlo simulation is an ensemble based things. So molecular dynamics is time and Monte Carlo has no time. That so as I stated repeatedly in this course, that it is very important to get an overall picture, because statistical mechanics involves a lot of techniques, a lot of beautiful stuff, and but soon when you start doing work or research, you tend to get lost into the details. Especially in computer simulation, you start what kind of numerical technique I'll use to propagate it, what kind of sampling, what kind of random number generator. So there are many details, but it is always makes sense to have the big picture in mind, so that you know from where you are starting and where to go, and you can figure out if you are making a mistake to get a overall understanding of what is expected, what kind of results I need to compare with experiments. Are my results correct? So these things are essentially to keep you on the correct state, and overall picture is required. So the computer simulation always has these 4 steps. Any computer simulation has these 4 steps. We start with we prepare initial configuration. I'll talk about preparing initial configuration example. Then the initial configuration often is very far from the system configuration that you want to study. So then that from the initial configuration, you have to run the system for a long time. Or in a Monte Carlo also, you have to make many moves to equilibrate the system that you need, the temperature, pressure, and density condition. This equilibration is a very important thing, because the equilibration brings the system to the state, macroscopic state so you start with the microscopic state in initial configuration, then you keep on evolving the system, keep on changing the system, so that you ultimately come to a state which I can call the system is in equilibrium, so that I can start now measuring the properties. So once it reaches the equilibrium, we do a production run. This is the run where we calculate all the quantities along the trajectory or along the sample run, and then we use those to get the numbers. So the production run generates the trajectories that to be used in analysis to obtain the experimentally observable results. Often the equilibration has to be longer than the production, because once equilibrium is done, production is reliable. So often the equilibration is 5 to 10 times longer than production run. So many times, for example, in a simulation of water of 1,000 water molecules, then your production run may be about 20 or 30 nanosecond, but your equilibration might be more than that, might be 50 nanosecond. So this is a very important thing to remember, that these 4 steps are always involved in. Okay, so yeah, about the initial configuration, I told you. For example, I want to simulate water. Then in order to generate the configuration of liquid water, which is random, with random positions of water molecules, random orientations, there are 2 ways to generate them. One is to put the water molecules one by one into the box. Other one, which is more easy to visualize, is start with an ice. Although you might be interested in knowing water at 25 degrees centigrade at ambient condition, but you can start with the ice, which is the structure of the ice at 0 degrees centigrade or a little below that, and so that ice allows you. So you put in a box around the ice. Now you increase the temperature. As you increase the temperature, the ice melts. This is what I was saying. Now, so ice served as the initial configuration. Now melting and running for a long time is the production, is the equilibration, so that after a long production done, the liquid water that you get has forgotten that it came from ice. Then we are in a position to start making calculations. So after that, and as I told you, within 1,000 water molecules, sometimes the production run starting from ice can be more than 50 nanosecond or even 100 nanosecond. So that the final equilibrium state has forgotten your ice and is a equilibrium state of the liquid water. Then we do maybe 10 nanosecond of the production run and keep track of all the positions and momentum down, and they use them, energy, position, momentum, orientation, to calculate the properties. The other is example seen is argon. We start with argon with FC crystal, and then I build the ice, and let's say I create an interface along the coexistence line of the liquid solid. Then you can see that on the left hand side we have the argon FC crystal. On the right hand side we have the random liquid, and the very sharp boundary between them. Similarly, if you want to consider a protein, then you start with protein data bank, which gives me a configuration of all the amino acids, and I take the X-ray crystal structure from protein data bank, which has all the positions and coordinates of atoms and molecules. And then if I want to study it in water, then I dip it in water and run again for a long time. so that I get equilibrated structure. Once I get the equilibrated structure, I start studying the properties of the protein. Same we do in DNA or the binary mixtures. So this is kind of explaining the steps of initial configuration, equilibration, production, and then the analysis of the trajectory. So these are here I am showing two trajectories in molecular dynamics, and there are two particles which are not very close to each other. The positions of the particles are projected on three-dimensional space where we can visualize them, and you can see that each of them seems to be a random haphazard motion, like what we call a random walk, the trajectories. The reason it is so random, look at that, because it contains the effects of interactions with all the surrounding molecules. And this is very important because this lot of information is contained into these trajectories. Now we'll go on the basic, very basic techniques of computer simulation, and and so there are the following techniques. One is the periodic boundary condition, and is minimum image convention. Then something comes minimum image convention they are all very closely correlated. The range of intermolecular interaction, which has to be finite, otherwise it's very hard to simulate. And then something generate random number generator as in Monte Carlo simulation. And this random number generator has to form a Markov chain. So these are all connected. That we are saying here, all the 5 techniques connected. And as I told you, huge amount of highly creative thinking and enormous amount of effort has gone into bringing this area of computer simulation, which is an active area of research in the present state. So let us talk about periodic boundary condition. Why do we need periodic boundary? It is, as you understand, the real system is Avogadro number of water molecules 10 to the power 23. But however, we cannot do that because we are going to solve the interacting systems. It turns out we can typically consider it for something like water, few thousand water molecules. Well, for demanding cases, sometime to resolve an issue, we might do larger systems. But routinely, we will do few thousand water molecules. And here we show that, but it's one huge problem a small system, that the fraction of surface of molecules on the surface scales as n to the power 2 by 3, where n is the number of particles in the system. So in a microscopic system, that's very, very small. 1 in 10 to the power 8 particle is in the system. However, in surface, for small system, for something like 216, which was the initial simulation of water molecule, was done with 216 water molecules. That is 16.5% of the particles on the surface. 1000 is still 10. So that okay, 216, 36, and 1100 particles, and this percentage on the last column, what percentage of particles on the surface. And you don't want that, because this creates a serious problem, because we do not want to study the surface effect. That has a different goal and different methodologies. We want to study the bulk properties, but if it is influenced so much by the surface, we cannot really trust it. So this was, and several other limitations or drawbacks of finite simulation was circumvented by very carefully and artfully implementing this condition called periodic boundary condition, which creates, kind of puts the repeated of the same your original system, but removes the boundary. It's done here. My real system are the red arrows, up, up, down, up, down. This is my Ising model. But now this two dash line, vertical dash line on the my red line is the defines the boundary of the system, but I don't want to have the boundary. So what I do, I replicate this on the left and right. Now see, on the left most spin, up spin is have a neighbor on the left hand side with the down spin. Similarly, has the neighbor which is on the left. So yes, this is, you may consider this little bit of artificial, but it's serves the purpose. We'll come to the artificiality. It serves the huge purpose of removing the boundary. So system is no longer bound. It doesn't have any surface. It is extended to infinite system. And then you will see that what are the limitations further, how we go about it. But it's true that it has certain correlations will be compromised, and but when the system is sufficiently large, maybe 1,000 or few thousand, then these surfaces, the particles which are on the surface, they fill the correlations. But if the correlation between one end of the surface to another of the surface is not long range, then for many purposes the periodic boundary condition, and so this is the continuity is made at the surface, and we at one stroke we remove the boundary. And now, and that in Ising model, the systems go they are fixed digit, but in this case in real liquid, molecules move around. Then there is one very beautiful thing that has been invented, that if a molecule goes out of the box, like the one on my top left in my shaded area, that is my original box, then another one which is an identical position placed in the periodic image will move in. So in this way, number of particles in the system, number of molecules in my system is conserved. This is done for every image. So every image retain the number of particles. So the particle leaves the central box, image enters through the exactly opposite side. This is again a very nice technique, but on the other hand, it has limitations, as you can realize. But as I'm saying that these limitations is not too drastic. Then periodic boundary condition, then suppresses correlations. For example, dealing in phase transitions, particularly near the critical phenomena, this periodic boundary condition creates a problem, because you are creating an image of a system when correlations go far beyond. So you are cutting off those long range correlations. That's why study of phase transitions is very difficult, but there are techniques again to circumvent them called finite size scaling, but we are not going to go into that. So the next technique is the minimum image convention, and this is another beauty. It's very again, when you are doing the periodic boundary conditions, you are creating a huge number of images. The system has become virtually infinite. Then two things come into play. A, if you are going to include interaction with the spins, then all the interaction with all these spins are not required. Or interaction of one molecule with all the other molecules that you created not required. And because of the finite range of the interaction potential, and more importantly, you do not want to interact with your own image. And here the rate is done. This is called minimum image convention, MIC. That's within the rate, my rate box, that I must cut out the interaction of my spin, that is one, the elliptical one, that should not interact with itself. Okay. So main system is showing here in this by double arrow on the bottom, and then we draw this thing so that now you within that, now you are interacting with my central spin is interacting with these two spins on the left and two spins on the right, but it does not interact with its own image. So that is the minimum image content, both periodic and real images, and particle must not see its own periodic repetition. Then another thing of the minimum image convention is another thing that works very well with MIC is the truncation of intermolecular potential. Many times we actually do not have to go all the way to minimum length of the minimum image convention, because intermolecular potentials are often short range, and the Eichler-Jones potential we might take up to third neighbor or so. After that, intermolecular potential becomes negligibly small. So when interaction potential is short range, then we need not consider interaction between all the particles. Then we can have a kind of a box within which we will consider the interaction. So this is then combined with the minimum image convention to take care of the finite range of the intermolecular interaction. So as I told you, there are many interesting techniques are developed, and this is and then random number generator, and particularly in Monte Carlo simulation, what do we need to do? We need to do many random moves, because we have to sample the configuration space, and we cannot let move in a correlated way. Then many offbit or many other configurations which are far from my initial configuration will remain unexplored. So basic idea then is to push the system into different directions randomly, so that my system samples maximum number of configurations, and this is done by using a random number generator, so that the positions and the velocities are changed of each atom or molecule are changed randomly by small amount. But then we of course have guidelines to see that whether we accept that configuration or not, and that is sampling that was developed by Metropolis and called Metropolis sampling, but we will come into that in the next lecture. So, but we need that for a very large number of random numbers. And one important thing, that the random numbers should not be correlated. So random number should not repeat itself. And this is called, when I have a sequence of random numbers where one is uncorrelated to the other. So we develop basically we develop a Markov process which has no correlation. So each random number and the previous one, next one, they are all completely uncorrelated with each other. And that's very important, so that I get to sample much of the configuration space. The transition from one microscopic state to another microscopic state, has to be as much uncorrelated as possible, so that I sample everything. Of course, that's not possible, because just giving push, you do not put it away of the configuration space, but we allow it to move in all directions. So while Markov chain is independent of each other, system is not independent. We should not mistake that. System remains correlated, but we push it in different direction, so that everything is and computer simulations done in reduced unit. I talked in many times in my class that because of the universality that allows it, rho star is rho sigma, sigma is the molecular diameter, rho is the number density, T star cavity by E. This dimensionless unit allows a transferability, that I can now compare a methanol with ethanol, but then I have to put them in the same dimensionless unit. And a rho star of ethanol will have different rho, because sigma is different. Similarly, methanol will be different. T star will be different because of the interaction potential epsilon. So it's very important. The dimensional unit, as I discussed, the law of corresponding states, allows you to explore certain aspect of universality. It is a very important thing. So final issue I discussed today's lecture is the force field, which is like interaction potential. As I said, Lennard-Jones is very simple. Even that was generated because of the Lennard-Jones did it by using the Mayer's expression of the virial coefficient, temperature dependent of the virial coefficient from equation of state, which was measured experimentally. But in for example, like water, we similarly have the equation of state. We have the diffusion coefficient of the water. Now there is oxygen, which is negatively charged, and two hydrogen, which are positively charged. We by a large know from quantum chemical calculations what could be charged. Then size. However, there are many things we are not taking into account when we are taking the two water molecules interacting and we pairwise additivity. That means 3-particle, 4-particle interactions are not taken into account. That has to be absorbed in my interaction potential. This game, this technique of finding a good interaction potential is called force field. Is a highly demanding and highly respected area of research now. Because once you have a force field, then you get the rest is now pattern is well set. So this is the force field. Once I get force field, I can do the computer simulation. But getting force field itself requires a lot of computer simulation, a lot of statistical mechanics, and so back and forth, back and forth. Then finally, we settled on a force field, and that then can be used for computer simulation. Okay, so take home message of this lecture is that we study complex systems with many more interactions. It really take the statistical mechanics in a huge direction. So to an extent, the modern success of statistical mechanics as a subject is hugely due to the computer simulations. And there are many books. My book is there, but then computer simulation of the Frankel and Smith, and then the Allen and Tildesley, number 3 Allen and Tildesley is a very respected book, and I strongly recommend. And you get a lot of materials on on in the internet and Google, and you can see many simulations, actually the trajectories, the configurations evolving through computer simulation. I strongly recommend you that you see some of these things in your